Hello everybody. In this video we're going to start the application of what we learned in the previous videos about the steam tables in real problems. So in this case we will start with the procedure just to know if you have a unit where you want to do mass balance on, and you want to get the information about the enthalpies from steam table. What can we do? This procedure is going to be very similar to the procedure we will follow in the next chapter. But in the next chapter we will be calculating the enthalpy using equations instead of using the steam tables in this case. Otherwise the procedure is almost the same. So the procedure starts with first the drawing the flow chart. So it's similar to what we do in mass balance. We need to draw a flow chart, put all the labels, put all the information that we need to have, and this includes all the all the parameters of interest. So in this case, we are interested in temperature, pressures, flow rate, and the material state, even either it's solid, liquid, or vapor. This is gonna make a difference regarding the calculations that we will do and the numbers that we are extracting from the table. And then if there is some flow rates are missing, we can do mass balance, um, so that we can calculate the missing flow rates, and then we apply the energy balance equation, use the tables to get the data for the calculations for the enthalpies, and then that's it. So in this case, since we haven't gone through any calculations of enthalpy, we just uh, covered the steam tables. So we are going only to deal with steam tables in this chapter, and in next chapters we will deal with the other materials and or other components, and if you have multi-component system, which is more than one component. In this case, we only deal with steam. There's just one point that I want to highlight here, which is regarding the mass balance calculations. So in real life, what we do in the calculations when we do mass balance and energy balance, we don't do them separately. And in general, we do calculations of mass and energy balance simultaneously. We solve the equations of mass balance with the equations of energy balance. This is going to be a more difficult task to do. You need to do the solution of the equations simultaneously, which is time consuming and requires a lot of calculations, especially if you're doing the calculations manually for the enthalpy. This would be a very tough task to do, especially if you have more than one component. So it's not easy. As we will see next chapter, you will have a lot of variables. It's not only the compositions and flow rates. You will also have the temperatures. You might have the pressure also part of it. So it's going to be hard to calculate. So what we do here is we get the mass balance done first. If there is a missing flow rate or a composition, we get the mass balance done first, and then we start with the energy balance. So I just wanted to make this point clear, just to have to give you an idea how the calculations are done. And this is, by the way, this is what happens in the simulation software, like Aspen Plus and Aspen HYSYS and all these simulation software. This is what the software do. They don't solve the mass balance separately and then the energy balance separately. They solve all the equations in addition to the equilibrium relations. They solve them all simultaneously. But this requires computational power, which is something that software can do for us. Anyway, so now let's take this example. We have steam at 20 bars absolute. Its temperature is 200 higher than the saturation temperature. So this means that it's superheated because its temperature is higher than the saturation temperature. It's fed to a turbine at a rate of 2000 kilogram per hour. So we know the turbine is a piece of equipment that is used to convert the pressure or any form of energy, like the hydroelectric power, like the I mean the power of water, the flow of water, or the flow of wind, or whatever the energy that we have. It can rotate the blades of the turbine and generate electricity. So here it's a steam turbine. So it operates using high pressure steam, and the turbine operates in adiabatic. We said adiabatic before means that there is no heat loss. And the effluent is saturated steam at 1 bar. So of course the steam will lose energy because it has high pressure and then it's turning the turbine, so the energy is lost and converted to output work. So we need to get the output work in kilowatts, neglecting the changes in kinetic and in potential energy. So first we need to draw the flow chart. So this is the diagram that we have. In this diagram we have the mass flow rate 2000 kilogram per hour, the pressure is 20 bar, the temperature is the saturation temperature plus 200. The pressure is 1 bar for the product. The temperature is saturated because here it says the output is saturated steam. I should have written here that this is steam because we should write the state of the matter. So this is steam, and this is steam, of course. It's superheated steam, and we need to calculate this work that is coming out of the turbine. So to do this, we need to start with the general equation, which is the open system equation. In the open system equation, we have 5 terms. The change in enthalpy plus change in kinetic and change in potential energies equals Q plus work. We have terms that are zeros here. First, we will neglect the change in kinetic and potential energy, so these 2 terms would be 0. Also, we are told that this is an adiabatic process, so Q equals 0. So the result is only 2 terms, which is delta H equals W. And we know delta H is the mass flow rate multiplied by H out minus H in. Of course, these are the specific enthalpies in kilojoules per kilogram. So if you multiply these in kilojoules per kilogram by mass flow rate, which is kilogram per unit time, so this is going to be energy per unit time. And then we need to find out the work. So we need to know the mass flow rate, the enthalpy in and enthalpy out. Mass flow rate is already given as 2000 kilogram per hour, so we need to find H out and H in. We know this is steam, so we can go directly to the steam table to calculate or to find out the values of H in and H out. So if you go to the steam table, we need to first find out which table we should be looking for the information in. This is superheated steam, and this is saturated steam. So if it's superheated steam, we'll go for the table or the steam table where we have the superheated steam information. We know here, based on the information that we know here, that it is 10 bars. No, it's 20 bars. It's not 10. I think this is a mistake. It's 20 bars, and the saturation temperature is higher than the temperature is higher than the saturation by 200. I edited the information in the problem, but I forgot to fix this. This is 200 Celsius, and this is 20 bars. So if you go to the 20 bars line, so this is the 20 bars. To know the temperature, we must check the saturation temperature first, because it's 200 Celsius more than the saturation temperature. So saturation temperature is 212.4. So the temperature of the steam is 200 degrees Celsius more than this, which is 412. We have data about 400 degrees and 450. So it should be somewhere between these two values that we have here. So this is the line of interest. First we go to the saturation temperature plus 200. So this is the temperature of the feed. And we have the information about 400 and 450. So to get the information about 412.4, we do interpolation, and by interpolation we use this relation that the slope is delta H over delta T equal delta H over delta T. We did this many times before, and we can find the enthalpy of the feed steam. For the product steam, it is saturated at 1 bar. So we need to get the enthalpy of saturated steam at 1 bar. We have one of two options, either to go to the steam tables where we have the saturated steam tables, or we can use this table, the same table, because in this table you can see the pressure of 1 bar is already included here, and the enthalpy of saturated steam is 2675. It's already there. We don't need to go to the other table, so it's already available. Luckily, and it's already available. So now we got the enthalpy of the feed, the enthalpy of the product. So what we can do now is to substitute in the energy balance equation. We have the mass flow rate in kilograms per hour, the two enthalpies that we have in kilojoules per kilogram. Of course, there is a very important point here that the delta H is the output enthalpy minus the input enthalpy. So the output enthalpy is the saturated steam at 1 bar. The inlet enthalpy is the superheated steam at 20 bar. So the output minus input would be negative, which makes a lot of sense because it's work done by the system on the surrounding, which is a negative work. So the work must be negative. Okay, it's work that's lost work. So this makes sense. So it cannot be a positive work, of course, here. So by substitution, this would be the value in kilojoules per hour, but we want this in kilowatts. And in kilowatts, we multiply it by hour over 3,600 seconds, and this is going to be the value in kilowatts. By the way, there is one other thing just to mention this. If you want to go for or you want to extract this number from the steam table, you can directly go here to the pressure table. This is 1 bar. The enthalpy is 2675.4. So it's the same. And I just want to make sure it's clear. So this is the same number here as this number here. It's exactly the same number. So in case you prefer to use this table, it's giving the same thing. But anyways, we're already using this table, so it's more time saving to use the table without going back and forth between different tables. Anyway, so this is all what we need to talk about in this problem. Next video we'll talk about, or we'll get another example to solve and to get more idea about these kind of problems. So I'll see you then, inshallah. Goodbye.